Hello, in this video, I'm going to show you guys how to set up a carburization model in Abaqus using the DANTE software. The DANTE software contains a set of subroutines that can be linked with either Abaqus or ANSYS to model the heat treatment process. Some common processes that can be modeled include gas carburizing, low pressure carburizing, induction hardening, liquid quenching, press quenching, temper, and many more. In this tutorial, I will set up a two-step carburization process using the 41XX material found inside our material database. The first thing that we want to do is create a working directory and open up Abaqus CAE. So I've already created a temporary folder here with the geometry file inside that we're going to use. So let me open up command prompt, change my directory, and launch the Abaqus version that I want to use. For this model, I'm going to be using Abaqus 2023. So with Abaqus CAE open, we can select standard/explicit model and import our geometry by going to File, Import, Part. So once this window is open, we can go to File Filter, select Step, and select the geometry file that we want to use for this model. Once this window opens up, we can go to Part Attributes and make sure we select Axisymmetric. So now that we've successfully imported the geometry, I'm going to save the model. I'm going to call this ring axis heat treat model. So the first thing I want to do, like any Abaqus analysis, is go to Assembly and create an instance of the part that we want to modify. So now that we have the instance created, we can go to Mesh, select Part, and create the mesh for this model. For a DANTE carburization model, we want to make sure that the elements on the surface of the geometry is finer than the elements in the core. And this is so that we can accurately capture the high carbon gradient for the carburization model. So to do that, we can select Seed Edges, box select the entire geometry, make sure all four surfaces here are selected, and click Done. So once the local seeds window pops up, underneath bias we can select double and change the minimum size from 0.5 to a smaller value of 0.15. We can click apply, and now we can mesh the part. So now that we have the part meshed, the last thing that we want to do is make sure that we change our element type from axisymmetric to heat transfer. So after we're done changing the element type, we can go back to part and create our different sets. So the first set that we want to create underneath the part module is the all elements set. So to do that, we can go to Tools, Set, Create, and I'm going to give this name all elements. Leave geometry selected, click Continue, and box select the entire part. So once we've selected the entire part, we can click Done, and our all elements set should be created. So the purpose of this set is so that we can assign the material that we want to use for this model to this all elements set here that we've created. So once we've created this set, we can click Dismiss and move on to the assembly module. So inside the assembly module, same thing as before, we can go to Tools, Set, Manager, and Create. The first set that we want to create underneath the assembly module is the all nodes set. For the all nodes set, we want to make sure that node is selected. We can click Continue and select all the nodes inside the part by box selecting. So the all nodes set will be used to assign the initial conditions for the carburization model, such as carburization temperature and base carbon. So with the all node set created, we can create another set, and this one will be called monitor node. We can select node, and this time instead of box selecting the entire geometry, I'm just going to select a random node on the surface of the part. So the monitor node will be used to keep track of a specific node, the node that we selected here, as the analysis is running. So this is an easy way to make sure that our values are correct and to double check whether we made a mistake inside our boundary conditions as we were setting up the model. So now that we've created the all node set and the monitor node set, we can dismiss. And the last thing that we have to do is go to Tools, Surface, Manager, and create our exposed surface set. So we can leave the type as geometry, click continue, and select the 4 surfaces here that we're going to assign the carburization boundary conditions to. So now that we have the exposed surface set created, we can click dismiss, make sure we save our model, and next we can go to plugins and open up the DANTE Model Builder. So before we make any modifications inside the DANTE Model Builder, I'm going to change the name of this model here. So by right clicking, selecting rename, and I'm going to give this AXE ring C to represent a carburization model. So once we've changed the name, the active model here should have changed too. So the first thing that we want to do is change the model type to carburization, and with that change we can create a new DANTE model. So if done successfully, up here at the top, the active model should have our model name with the phrase carburization afterwards. So after we created the new model, we can go to the next tab, the materials tab. So this tab is where we're going to assign the material to the all elements set that we created earlier. So to do that, we can click underneath material name and select the S41 material that we're going to use for this model. For the all elements set, we can select the all elements, or for the element set here, we can select the all elements set that we created earlier. So with those two options selected, we can click add material section, and it should have successfully updated inside our model tree. If we take a look at the section, we see a new section created, and underneath part, we see a new section assignment. So next, inside our DANTE Model Builder, we can go to the Steps tab. The first thing that we want to do is select Monitor Node and select the Monitor Node set that we created earlier inside the assembly module. So the Steps tab is what we're going to use to define the time period for each of our carburization steps. So the first step, I'm going to name Carb Step 1. We can leave the description blank, and for previous step, we can select Initial since this is the first step. The first carburization step will be a time period of 8 hours, but since DANTE uses seconds as its units, we have to convert the 8 hours to seconds, which will be 28,800 seconds. So the rest of the values here, the maximum number of increments, carbon change, the initial time increment, and minimum time increment, we can leave as default. So all we have to do is click Create Step. Since this is a 2-step carburization process that we're going to be modeling, we have to define the time period for the second step now. So underneath step name, we can give a new name, so Carb Step 2. Leave description as blank. And for previous step here, I'm going to be using Carb Step 1 as the previous step. For the second carburization step, instead of 8 hours, we're going to be decreasing the time period to a period of only 3 hours long. So 10,800 seconds. Again, we can leave the rest of the values here as default and click Create Step. So now that we have the two carburization steps created, we have to define the initial and boundary conditions for this model. So we can move over to the initial slash boundary conditions tab, and the first thing that we want to do is click the Add Initial Condition button here. For a carburization model, there are two main variables that we have to modify: the carburization temperature and total carbon weight fraction. So the first thing that we have to do, let's make sure that initial is selected for the step. Make sure that carburizing temperature is selected, and we can give a constant value of 925 to represent the carburizing temperature of 925 degrees Celsius. So we can click Apply, and again, inside our model tree here, in the bottom left, we should see a new predefined field for the first carburizing temperature that we defined here. Next, let's change the field type to total carbon weight fraction, and this represents the base carbon inside our material. So the material that we're going to be using is the 4120 material, which means it has a base carbon of 0.2%, and since this is in weight fraction, we will be typing 0.002. The last thing that we want to change is the carburizing temperature for the second step. So to do that, underneath steps here, instead of initial, we can change this to carb step 2 and change the field type to carburizing temperature. Instead of the 925 degrees Celsius carburizing temperature that we used before, we can give a constant value here of 875 degrees. So once we've defined the carburizing temperature for step 2, we can click apply, dismiss, and if we see 3 predefined fields here, that means we've successfully defined the initial conditions for each step, so we can exit out of this window. So once we've defined the initial conditions, the next thing we have to do is define the carburizing boundary conditions for our model. So to do that, we can go to Add Interaction, and this new interactions window should pop up. For a carburizing model, there are 2 main values we have to define: the constant reaction factor and the carbon potential. The constant reaction factor can be thought of as the HTC for a thermal analysis. So this controls, the constant reaction factor controls the speed at which the surface of the part reaches the carbon potential that we're going to define later. For a gas carburizing model, since the time periods are extremely long, we have an 8-hour step and a 3-hour step, the constant reaction factor has little to no effect on the final result of the analysis. For a low pressure carburizing model, the constant reaction factor has a more significant impact since the boost steps can be as short as a minute long. So by default, typically inside a DANTE gas carburization model, we use a value of 0.005. For carbon potential, for the first step, we're going to use a carbon potential of 1.1%, and since this is in weight fraction, we're going to type 0.011. So with those 2 values defined, we can click apply, and that's our boundary conditions defined for the first carburization step. So for the second step, we can go to carb step 2 here and leave the constant reaction factor the same, and the only thing we have to change is the carbon potential here. So for the second carburization step, we're going to use a carbon potential of 0.0085 or 0.85%. So we can click apply, and that should be our carburizing boundary conditions applied for both steps. So we can exit out of this page and double check our model tree to make sure that we have 2 interaction properties here defined for each step. So the first step, if we double click, we can see the reaction factor defined at 0.005 and the carbon potential of 0.011%. And for the second carburization step, we see the carburizing potential of 0.0085. So now that we have the initial conditions and boundary conditions defined for our carburization model, we can save, go back to the Models tab, and submit the job. So once the job has been successfully submitted, we should see a message here inside the message window. Yep, so pre-processing is now complete, and now job monitoring output is now available in the viewport. Yep. Since this is a smaller model, this job finished extremely fast, but we can take a look at the working directory here. So there's a few new files created once we've submitted the job. One of the files is the .sta file here. If we open this up, we notice that this outputs the monitor node, or the value, the carbon content for the monitor node that we defined earlier inside the model. So under degree of freedom monitor, we can see a value of 0.00201. So this represents the carbon content at that specific node. And since we define a base carbon of 0.002, the value here of 0.00201 does make sense. If we scroll down to the bottom, to the end of step 1 here, line 103, we can see that the node reaches the carbon content of 0.011, which represents the carbon potential that we gave the model of 1.1%. So again, the results seem reasonable. And if we take a look at the very end, so the last step, step 2, the value at the monitor node drops back down to 0.0085 or 0.85%. So the values inside the STA file, the status file, seem reasonable. So we can close out of here. Go back to the Abaqus CAE, close out of the Dante Model Builder, go to the Visualization tab, and open up the ODB file that was newly created. Once we have the ODB file, once we've opened the ODB file, we can click Plot Contour, and we can take a look at the carbon profile at the very end of the analysis. So for a Dante carburization model, we take advantage of the heat transfer model that Abaqus has, and we replace the NT11, which normally represents temperature, with carbon. So as you can see in the legend here, we have a maximum carbon value of 8.7 e to negative 3, so 0.0087 carbon content, or 0.87%. And our core here remains 0.2%, which is the base carbon that we defined. If we want to take a look at the carburizing temperature, we can go to the drop-down menu here and select SDV temperature. So for step 2, we define a carburizing temperature of 875 degrees Celsius. And if we go back a step to step 1, we notice that the temperature here is 925, which is correct. So that concludes our Dante carburization model tutorial for an axisymmetric ring. Thank you everyone for tuning in. If you have any questions regarding the tutorial or our software, you can visit our website at www.dante-solutions.com or contact us at support@dante-solutions.com. Both links will be in the description. Thank you.